Hi everyone, so we are back talking about the big three, Kepler, Galileo, and Newton. And just to review for you, Kepler really showed us the mathematics of a sun-centered universe and of orbits, but he didn't explain why that math worked. Galileo brought in evidence-based experimentation and showed how heliocentricity worked and how orbits worked, but he didn't explain why they worked. And Newton later finally brought it all together and explained why a sun-centered universe worked and how orbits functioned. So just to review for you, the laws of planetary motion by Kepler, you know the first law was about ellipses. You know the second law is about sweeping out area in equal times. And the third law is about the orbital period and its relationship to basically the radius of the orbit. And all of those were great mathematical constructs. Galileo was a friend of Kepler and supported his notion of a sun-centered universe and started talking about gravity. And when he talked about this, he talked about inclined plane experiments that he could do. This is a replica here of an inclined plane that Galileo used. It has in here bells that would chime to give another bit of evidence for his timing. And he would time the seconds by his pulse or by a pendulum that went by, because clocks in the 1600s were not that reliable, but pendulums were more reliable. Galileo was the first one to talk about acceleration as change in distance over change of time. And he was the first one who talked about an object at rest stays at rest and an object in motion remains in motion. This idea actually went back to Aristotle, but needed some framing. And Galileo added to the framing by saying that the object in motion remains in motion in the same direction at a constant speed unless disturbed. And generally the disturbance was friction. So that's Galileo's take on it. And then that was referred to as his law of inertia. Inertia meaning resistance to change, meaning that if an object was at rest, it stayed at rest. If an object was in motion, it stayed in motion. It was resistant to change, law of inertia. Now, this helps you out a little bit. Galileo took that experimentation and moved it forward in a big way. And he was saying that, and he was supporting a sun-centered universe by saying that we on Earth are forever orbiting at a constant speed on a planet that's forever orbiting at a constant speed. That's why we don't feel the movement of the orbit. And I give you that notion there because when you accelerate or when you decelerate, then you notice the speed. While everything is constant, you can drink the soda just fine. But when there is a change in speed, you notice the speed and, bad things happen. So Galileo was able to support Kepler's calculations and support Copernicus in the heliocentricity by saying this is why we don't feel ourselves moving, because we're all moving at a constant speed. On top of that, you know that Galileo pointed out Jupiter's 4 moons, and if Jupiter had moons, it wasn't just the Earth that was special and had moons. So that supported heliocentricity, and the observations he made of those moons supported Kepler's work on orbits and on ellipses. And on top of that, Galileo found that Venus had phases, so that meant that the sun needed to be in the center of the universe in order to show those phases that Venus showed. Now, bring in Newton. Newton explained the why of all of this math and all of these observations. Newton was born a year after Galileo's death. And as he was on a school break during the Black Plague, sound familiar? 1665 to 1667. He went home because school closed, sound familiar? And he considered the work of Kepler and Galileo and explored optics, explored gravitational forces, thought about them along the same way for waves, and we'll be exploring light waves later on. And he looked for patterns on how light waves were like gravitational waves. And he invented calculus to define patterns in the data. So, really useful break during a plague. Really inspiring. Newton's work actually generalized gravity to encompass not only what we see on Earth, but what we see in the entire universe. And you can even go down to a molecular level with Newton, or you can go all the way up to a cosmic level with his gravitational work. So it is quite amazing, and we're going to look into his laws of motion and his universal law of gravitation. He revolutionized physics and revolutionized scientific thought. Newton dovetailed onto Galileo and the inclined plane experiments and took it out another level from Galileo, saying that if planets and moons are masses that move forever, but in curved lines, then there is a force acting to create those curved lines. Galileo was big on friction, but Galileo was even beginning to hypothesize that there was no friction in space. So what was the force? And Newton started studying the motions of bodies and the forces that act on those bodies. His first law is not a mathematical law. Like we mentioned, there are natural laws which have so much evidence behind them that we look at them as theories with a mathematical bend to them, a natural law. Basically, Newton took Galileo's law of inertia and tweaked it a bit. And he tweaked it to say that an object in motion tends to move in a straight line. So he just tweaked it. Galileo said it moves in the same direction. Newton tweaked it to say it moves in a straight line unless another force acts on it. So the pink arrows here represent the force that gets the ball rolling, and the green arrow is the force that makes it change its direction. Really important point here. And what we wanted to point out here was that Newton has the big story about the apple. And the apple falls into the object at rest part of the story. Now, Newton's apple was at rest due to a balance of forces. The tree branch extended up and supported and provided a force for the apple to stay up. The apple was always being pulled down by gravity, and those forces were balanced. something happened. Maybe there was a gust of wind, another external force. Maybe there was a disease on the trunk, and so the limb weakened and couldn't withstand the gravitational force. But some external issue happened to change and unbalance the forces, and the apple fell down because the gravitational force was greater. In addition to that, Newton's brilliance is that he related the object at rest to the object in motion, so that he saw that planets were objects in motion. And the brilliance that he had was that there was an initial force that got the planets rolling. And that initial force was never going to stop because it was an object in motion. And that initial force was probably the foundation or the formation of those planets. And we don't even know how planets formed. We have hypotheses, and the best one is that they probably formed from a violent collapse of a molecular cloud. We'll get into that later. But at any rate, that formation moved the planet Earth and every other planet in our solar system in a straight line at a constant speed. And then an external force, the sun's gravitational force, changed the direction of that planet, our Earth. So think of it this way. The initial force was the formation of Earth, sending off our planet Earth in a straight line at a constant speed. The sun formed, had an enormous amount of mass, and developed a gravitational pull that changed the direction and that pulled on the Earth and pulled it toward. So if you balance out the horizontal velocity and the gravitational velocity, you wind up with a curve. Every time the planet moves horizontally, it gets pulled, horizontally and pulled, horizontally and pulled. An orbit is like a free fall, but you're always missing Earth. And the reason you are always missing Earth is because your initial force of formation is balanced by your gravitational pull. An orbit is like a free fall that always misses. Now, like I explained, Newton's genius was that he could look at the object at rest and the object in motion, and he could isolate gravity in both cases. So the same gravity pulls apples down toward the center of the Earth when it's unbalanced, and the same gravity pulls planets toward the center of the sun when it is balanced. Think about that. And I'll see you on the other side.